In this video we'll show machine learning implementations on different datasets using Python. The mean face of a set of face images refers to the average face computed from a collection of face images. This concept is often used in facial recognition and computer vision applications, particularly when using techniques like principal component analysis, PCA, for face recognition. Steps to compute the mean face. Collect face images. Ensure that all face images are aligned and normalized to the same size and format. Convert images to vectors. Each image is flattened into a one-dimensional vector. Compute the mean face. Calculate the average of all the image vectors. Reshape the mean vector back to image. Convert the mean vector back to the original image shape to visualize the mean face. Problem formula. Eigenfaces is a technique used in facial recognition that involves using principal component analysis, PCA, to decompose face images into a set of characteristic features or eigenfaces. These eigenfaces represent the principal components of the distribution of faces, capturing the most significant variations between different face images. How eigenfaces work. Data preparation. Collect a dataset of face images, typically aligned and resized to the same dimensions. Convert each image into a 1D vector by flattening the pixel values. Compute the mean face. Calculate the average face, mean face, from the dataset by averaging all the face vectors. Subtract the mean face from each face vector to center the data. Perform PCA. Construct the covariance matrix from the centered face vectors. Compute the eigenvectors, principal components, and eigenvalues of the covariance matrix. The eigenvectors corresponding to the largest eigenvalues represent the directions of maximum variance in the face space. These are the eigenfaces. Form eigenfaces. Each eigenvector, eigenface, is reshaped back into the original image shape, representing a pattern that is common across the faces in the dataset. The eigenfaces are ordered by their corresponding eigenvalues, with the first few eigenfaces capturing the most significant features of the face dataset. Face recognition. Project new face images onto the eigenface space by calculating their dot product with the eigenfaces. The resulting coefficients form a feature vector that can be used to compare and recognize faces. Metrics with different principal components method. PC equals 90, PC equals 103, PC equals 200, naive Bayes 76.67, 77.50, 69.17 KNN 90.83, 90.83, 90.00. Random forest, 93.33, 92.50, 91.67, logistic regression, 96.67, 98.33, 98.33, SVM, 96.67, 96.67, 96.67. Analysis. 1. Naive Bayes. Performance trend. The performance slightly increases from 76.67% to 77.50% when increasing the number of PCs from 90 to 103, but drops to 69.17% with 200 PCs. Interpretation. Naive Bayes shows a small improvement with more PCs initially, but eventually degrades with too many components, possibly due to overfitting or the added noise in higher dimensional spaces. 2. K-nearest neighbors. KNN. Performance trend. The performance remains stable at around 90.83% regardless of the number of PCs used. Interpretation. KNN's performance is robust to the number of PCs, indicating that the algorithm's performance is not highly sensitive to dimensionality changes in this range. 3. Random forest. Performance trend. Performance decreases slightly from 93.33% with 90 PCs to 91.67% with 200 PCs. Interpretation. Random forest performs well with a moderate number of PCs and shows a slight decline with more components. This could indicate that beyond a certain number of components, additional PCs may introduce noise or redundant information. 4. Logistic regression. Performance trend. The performance improves from 96.67% with 90 PCs to 98.33% with 103 PCs, and stays at 98.33% with 200 PCs. Interpretation: logistic regression benefits from more PCs up to a certain point and maintains high performance even with more components, suggesting that it can leverage additional features effectively. 5. Support vector machine, SVM. Performance trend: the performance remains constant at 96.67% across all PC configurations. Interpretation: SVM's performance is consistent regardless of the number of PCs, indicating that it is robust to the dimensionality of the feature space in this range. The data provided shows the accuracy metrics for different classification algorithms with and without principal component analysis, PCA, across various training test splits. This comparison helps evaluate how PCA affects the performance of each algorithm. Analysis. Naive Bayes. Performance trend: the accuracy remains unchanged at 92.5% with PCA for the 90:10 split. Performance improves from 87.5% to 90.0% with PCA for the 80:20 split. The accuracy increases from 73.33% to 77.5% with PCA for the 70:30 split. Interpretation: PCA shows a positive effect on naive Bayes in less favorable splits, helping improve accuracy when the training set size is smaller. K-nearest neighbors, KNN. Performance trend: accuracy remains unchanged at 90% for the 90:10 split with PCA. Performance improves from 91.25% to 92.5% with PCA for the 80:20 split. Accuracy slightly increases from 90.0% to 90.83% with PCA for the 70:30 split. Interpretation: KNN benefits from PCA in the 80:20 split, showing a notable improvement. The performance remains stable for the 90:10 split and slightly improves for the 70:30 split. Random forest. Performance trend: accuracy improves significantly from 90.0% to 100.0% with PCA for the 90:10 split. Performance increases from 93.75% to 95.0% with PCA for the 80:20 split. Accuracy slightly decreases from 93.33% to 92.5% with PCA for the 70:30 split. Interpretation: PCA provides a substantial improvement for random forest, particularly with the 90:10 split. However, there is a minor decrease in performance with PCA for the 70:30 split. Logistic regression. Performance trend: accuracy increases from 95.0% to 97.5% with PCA for the 90:10 split. Performance remains the same at 97.5% with PCA for the 80:20 split. Accuracy improves from 97.5% to 98.33% with PCA for the 70:30 split. Support vector machine, SVM. Performance trend: accuracy remains unchanged at 95% with PCA for the 90:10 split. Performance remains unchanged at 97.5% with PCA for the 80:20 split. Accuracy remains unchanged at 96.67% with PCA for the 70:30 split. Interpretation: SVM's performance is unaffected by PCA across all splits, indicating that the dimensionality reduction does not impact its performance. Summary. Best performance with PCA: logistic regression shows the highest improvement with PCA, followed by random forest and naive Bayes. Stable performance: SVM exhibits stable performance regardless of PCA, suggesting it is robust to changes in the dimensionality of the data. Mixed results: random forest shows mixed results, with significant improvement in some cases, but a slight decrease in others. It looks like random forest with 103 principal components, PCA, and a 90:10 split on the Olivetti dataset yields a perfect accuracy of 100%. This suggests that this combination of PCA components and dataset split is highly effective for this particular dataset and model. Why this might be the best fit. Dimensionality reduction: PCA with 103 components likely captures the most important features while reducing noise and redundant features, leading to better performance. Random forest: this ensemble method is robust and effective for a wide range of datasets. With the right number of PCA components, it can achieve high accuracy by leveraging multiple decision trees. Dataset split, a 90:10 split provides a substantial amount of training data, which helps in building a robust model, and a sufficient amount of test data to evaluate the model's performance. Next steps. Validation. To ensure that this result is consistent, you might want to validate the performance by testing with different random seeds or cross-validation techniques. Model tuning. Explore other hyperparameters of the random forest, such as the number of trees and maximum depth, to see if further improvements can be made. Comparison. Compare the performance with other algorithms and PCA component settings to confirm that this configuration is indeed the best for your use case. Visualization. It might be useful to visualize the impact of PCA components on model performance and the decision boundaries learned by the random forest model. Conclusion. Use of PCA improved the accuracy metrics. Project enhancement idea. Identify smile and no smile face / identify male and female.